Hello and welcome. Hello and welcome to everyone. So this is the third live session where we will be discussing about the structural vector regression. So in the last live session, few of the students you have asked about the structural vector regression. So taking up that question, we will discuss about the structural vector regression. So basically, the structural vector theoretical part we have covered in the recorded lectures. So here we'll be taking an example of a structural vector regression and how we can estimate that in R using R, and also we'll be discussing about how we use that for the policy applications. So as we have discussed earlier, that vector regression is the basically multivariate time series model where we assume that all the variables are endogenous. Basically, we do not categorize the variables into exogenous or endogenous variables. In the system, we have all the variables treated as the endogenous. Basically, if you have three variables, all three variables affect each other and its lag also affects each other. Therefore, we turn into the vector regression. However, in the vector regression, what problem we have that it is considered as a theoretical model. The reason for this consideration is that in vector regression, the restriction which we derive is based on basically statistical conditions, not from the theory, and which was considered as one of the key weaknesses of the vector regression model. Then later on, the economist has developed structural vector regression. Here, basically the structure term refers the conditions which we derive from the economic theory, not from the statistical theory. So that's the basically difference. And the structural vector regression is quite useful for the policy analysis, especially for the monetary policy and the fiscal policy analysis. So today we'll be discussing an example of the monetary policy analysis. All of we know that the monetary policy basically done by the central bank to control the inflation and also the output. So the key objective of any central bank is to have stable and low inflation and stable and sustainable high growth. However, there is often a very critical task to maintain these two. So whenever we have inflation, monetary policymakers take the decision to contain the inflation, and whenever we have low growth, monetary policy again take its stance to enhance the economic growth. For that reason, the monetary policy is very key to maintain a high and stable economic growth and low and stable inflation. So here, using the structural vector regression, we'll see how that monetary policy, if there is a change in the monetary policy, how the inflation and output reacts. So for that, we have taken the three data. So basically, you can see here, this is the R script basically we will be using here. So as usual, we have created a project, which I have named the SVAR project. So here you can look it up that this is the structural vector regression project we have. Then this is the data we have. So this data is in the CSV format. So first thing, let us attach all those packages from where we will be using different functions. So here the first package is URCA, which is basically to conduct the unit root test. And how we conduct a unit root test, how we make the inferences, those we have discussed earlier. So the similar steps, similar process we'll be doing here. And then we have the package VARS, which is from this we'll be using the function to estimate the vector regression. Then the package T series, which is basically to convert the data into the time series format. And we'll be also using the TS Studio package, and we'll be also using the forecast tidyverse, and then we'll be using the another package which is known the structural vector regression. So again, if all these packages are not installed into your system, then we have to use the function install packages. Then in double quote we'll write the package name, for example as where. Then we have to use the run, then it will install the packages. Here in my system already I have installed all the packages, so I'm not going to install again. However, to use that, I have to attach all those packages. So to attach all those packages, I will be using the function library, which already we have discussed. So here we have attached that. So let us uh, run all those. So here the library will using, so all those packages have been installed, attached into the this session. Once we have installed that, then we will be using the function read underscore CSV to import the data which we have installed into the data file name as the data is var.csv, which you can observe here. It is in the that particular folder we have. So once we have that, so now what we can see, so I have used this spec function to upload the data, to bring the data into the R system. Then I have named that as the macro CSV. Let me clean here. So let us see here, once we run that. So here you can see in the left top panel that now if an object by name the macro has been created, which we have 81 observations and the 4 variables we have. Let us see what are the variables we have here. So once we run that, you can see here. So basically, so if we have had here, so here you can see that first we have first column is date, second column is output cap, third column is RRP, which is basically interest rate, and CPI, basically consumer price index. So these are the variables we have. Now all of that I'm converting into the time series data. So for that, what we have here, the name of the time series column is Y. Here TS is basically to convert that into TS. Then first, which data we wanted to convert into time series. So here we have the macro assessor sign dollar. Then here on that we have basically used this gap because there is the gap between the output and the gap. However, we know that in the R, we have the convention that there should not be gap between the names of the. If you have, then we have to put this tick sign on that. Then the time series, so from where it is started, it is starting the 2000, the first quarter basically. So here we have given frequencies 24 because it is a quarterly data. And it's starting with the first quarter. So let us run that. So here we can, so you can see that here this Y has been created, Y variable, which is in the time series character and is starting from 2000 to 2020. Similarly, here pi, basically we are representing inflation, and here the macro and CPI. Now you can notice here we don't have any tick sign on that. The reason is that because it is a one name without any gap here. So if I'm running here, then you can see we have pi as well as R. So all three data has been converted into a time series data. Now let us use the time series plot to plot all three figures here. So TS plot, that is the time series plot. Then we have the which data we wanted to plot. So what will be the title of the plot? Then what will be the title on the x-axis? And what will be the name on the y-axis? So let us run this. So here we can see that here we have this time series plot. So this is the time series plot we have of the time and output. So similarly, we can plot the here inflation rate. So this is the inflation rate we have here. So this we can see here from 2000 to 2020, we have the inflation rate. Similarly, we can plot the interest rate. So here we have the inflation rate, which is again, you can see from 2000 to 2020, and all these are the quarterly data we have. So, and obviously we can observe these are the non-stationary data. However, to make it non-stationary, we have to differentiate and all. So before all that, what we will do, we'll make it as we'll use the unit root test to test that. So already we have discussed how to test the unit root, how to use the package URCA to conduct the unit root test, different unit root test, that is the Dickey-Fuller unit root test or augmented Dickey-Fuller unit root test or the KPSS or the Phillips pattern, all those unit root tests we can use. Even we have already discussed in the previous lectures that we can use the GWAT unit root test. So once we see those tests, then we can have this. So once we have, then how it deviates from the vector autoregression. In the vector autoregression, directly we can use the function vector autoregression. However, here we wanted to put the restrictions on the coefficients, that is, the continuous shock is there, how the variables react. So for that, we derive the restrictions from the theory. So already we have discussed there are the three types of restrictions we have. Short run, long, and the long run. In the short run, we have the A matrix and the B matrix, which we have discussed in the theoretical lectures. So here we are taking the example of the short run A matrix. So basically here we have the three variables that will be 3 by 3 variables. Now, the restrictions, so what will be the basically restrictions? So to have the restrictions, basically we have the 3 by 3 variables. That means we want to put here restrictions based on the theory. So what is the basically theory says that if we give the continuous shock to the output, then output should react contemporaneously. However, it may not have impact on the policy rate, and it may have effect on the inflation after a one lag. So basically, if we make a matrix, a diagonal matrix, so what we may have so let us say we have a matrix here. So then what we'll have, let us say here we have the output gap, and here we have inflation and here we have the policy rate R. Uh, then output has impact on that, and here we don't have compress effect, and here also we don't have compress effect. However, here we have effect on the output, but we do not have effect on the inflation, and here we have no effect on that. So this, and here we have. So what does basically it mean? It means that when we give a shock to the output, it has effect on it contemporaneously on its own leg. But on the inflation, it and its own. However, so here basically we'll have YT, and here we have inflation, and here we have R. So this shows that here, if we give a shock to the output gap, contemporaneously it have effect on inflation and rate of interest. However, if we give a shock to the inflation, it does have effect its own, and it has effect on the policy rate, but it has effect on the output gap with a lag, but it does not affect on policy rate. Similarly, if you give a shock to the policy rate, it has effect on inflation and output with a lag. It does not have contemporaneous effect. So that's the basically the restriction we are putting. In short, we are putting the restriction that if we give a shock to the output gap, it contemporaneously affects both inflation and the policy rate. However, if we give a shock to the inflation, it has contemporaneous effect on the policy rate, but not on the output gap. However, if we give the shock with the policy rate, it does not have any contemporaneous effect on the output gap inflation, but it does have effect with the lag. So that's basically we are creating this matrix. So how to create this matrix in R? So so to make this restriction on R, so what basically we'll do here, we have this. So we are creating a mat, that is we are getting diagonal matrix a 3 by 3. Then we are putting restrictions a mat 2 1 NA, a mat 3 1 NA, a mat 3 2 NA. So let us see the same structure we're having here. So here, then let us print this. So you can see here this. So here this NA basically will estimate these coefficients. So that these are the restrictions we are putting. So these are will be estimating here. So once we have created the restriction matrix, now we have to build the model. So first we are combining those time series into a one data set. So that data set we are calling as SV, and here we are using the function cbind to bind the column. So let us say cbind the column. So here we have SV. So you can see this SV, this how this looks like. First Y, then inflation, then rate of interest. This is the basic ordering of variable we are doing. Then instead of pi ry, we are giving the names output gap, inflation, and RRP. So that is the column names SB. So here we have done. Now, if you look here, so what we have output gap, inflation, RRP. Here, RRP is the basically policy rate we have. Now, once we have done that, the first task in the total regression is the nothing but selection of optimal line. So for that, we have the function where select. So we'll be using that function where select to choose the optimal line. So here, the lag select is the object we are creating where we will be saving those information. So here we are using the where select function. Here the data is SV. Maximum lag we are giving the 8 because it is quarterly data. So 8 lag means 2 years. In most of the macroeconomic, 2 years is enough to have the policy response. Here type both. So basically we are giving here that it should have both the constant and trade as well. We have. So we have selected that and we have created a lag select. So here you can say all those information has been saved here in this object. Now from that, we are using that from the lag select, we are using the selection based on that, then we are creating this. So here you can see all the information AIC and Quenon, Schwarz criterion, and FPE. All these criterion is giving us the same lag, that is the 5 lags. However, note that it's not necessary that every criteria will give us the same lag. It may differ. Then, which criteria should choose? It depends our subjective decision, which we derive from the theory. Usually, the rule of thumb in macroeconometric modeling, what we are assuming that SC puts more restriction, it gives more parsimonious model, whereas the AIC gives a less parsimonious. So, if you have the large enough data, then it is the AIC is preferred. If you have the small sample, then usually the SC is preferred. So usually SC gives a lesser number of lag, AIC gives a larger number of lag. How in this particular situation, all that information criteria gives us the same lag. So once we have choose that, now is basically we are choosing the criteria here. So here we can see all this criteria, all this information. The rule is that the minimum the value that lag will be choosing. So that's the basically. And here you can observe the minimum is basically here we are giving it this. So once we have chose that, then we are basically choosing 5 as the minimum lag, optimal lag. So here we are creating a model. Remember, to estimate the structural vector autoregression, first we have to estimate a reduced vector autoregression model. So for that, we'll be using the function vector autoregression. So in this vector autoregression model, we estimate and we save the results into the model 1. In that, what we are having, first we are giving the data set name, that is the SP, then lag length, that is the Pmax, seasonal effect we are not including, exogenous variable we are not including, type constant. So basically, we are not including the trend, we are including only the constant. So once we estimate that model, then we'll use that where estimated reduced form model to build the structural vector to regression model. So here you can see that as where model. So here again, the function is as where, then estimated model 1, so which we have stored here. Then this is the basically restriction we are putting AMAT. So with the restriction is here we have stored into the matrix named AMAT, which is basically here we have. Then BMAT, we are not putting any BMAT restriction. Hessian is true option we are giving. That estimation method is scoring and direct. So now let us estimate this model. So once we estimate the model, we have stored that model into SPR model. So now let us see the model. So this is the estimated matrix we have. So you can see here, all three here we have the diagonal matrix, then these are the coefficient we have estimated 0.211, 0.981, and here negative 0.11. Now, once we have estimated the model, then the first thing after estimating model is to look for the diagnostic test, which already we have discussed in the previous lectures. So what are the diagnostic tests we have? So that we can uh, do here. Then next is once we do the diagnostic test for the autocorrelation, heterostrategy, all those things we've done, which we have discussed in the previous lectures. So once we are satisfied, then we can see the policy response. So in the policy response, as we have discussed earlier, basically we rely on the two tools, that is the impulse response function and the variance decomposition. So we'll be using these two tools, that is the impulse response function and the forecast error variance decomposition, to see that how it reacts the shocks to the different models. Here, since we have three variables, so basically we will have 9 impulse response functions that we will give the shock to one. All three variables will react. Because we have the three variables, we will be giving the three shocks, then we'll have the 9 impulse response function. However, here, for the sake of example, we are giving only shock to the output gap, and then we are looking the response of all three variables one by one. So that can be controlled by using the function here impulse response. So let us say here we are storing this response and the impulse, then we'll plot this here. So the function is IRF. The model on which based on which we will be having impulse response function, that is SVR mode 1, which we have stored here. Then impulse, that we are giving the shock to the output gap. Then response, we are looking of the output gap. And we'll plot here. Now, let us say if we wanted to give the impulse to all the variables and we wanted to see the response of all the variables, then here we don't have to write anything. So it's better to look one by one, because we'll get the larger images and it gives better interpretation. So here the idea is we are giving the shock to the output gap, then see the response of output gap based on this estimated model. So let us do that here. So we estimate, then we plot. It takes a little time depending on that. So here we have this. So here we are giving the shock to the output gap. Then you can see here we have, once we give a shock to the output gap, then there will be more output gap, means basically the production increases. So here we can see that as we give a shock continuously, it increases almost by 100% or 1 unit here. Then slowly it decreases, then it increases and further decreases. So a cyclical behavior we have. So that means a positive shock in the output gap creates a positive change. So if we increase the output, it further increases the output. So basically, it expands output. So that's what we have, which is basically as per the theoretical expectation. So if you give the shock to the economy, if you increase the output, then in the next period the output will increase. However, over the period, the time that effect reduces. So that's basically what we have here. Now let us see that if we give the impulse again output gap, then how the inflation reacts. So from the economic theory, what we know, if we give the output is increasing, that means the economy is expanding. So then obviously inflation also expected to increase. So what we call the overheating of the economy. So let us say, do we have the theoretical response here? Does it turn out to that? So again, IRF, this estimated model, we are giving shock to the output gap. And here we are looking the response of the inflation. It takes little time to calculate the impulse response function, then plot it. So now if you look here, so as per expected theory, we have the inflation here. Okay, as we are giving shock to the output, the inflation is increasing, then slowly it decreases. That means as the output expands, there will be heating of the economy and the prices are increasing, which is the basically theory says us if that happens, inflation would be higher. And that's what basically our model also predicts. So one thing to notice here, the black line is basically response, and these two are the basically standard errors. So here you can see obviously it is within the standard or error boundary we have, and we can see here that a positive shock into the output gap increases the inflation. Now let us see what happens, the, how the monetary policy reacts. So you can guess. So then I will reveal at the, we'll see how this model reacts. So again, same function IRF we are using, and we had the impulse that is shock we are giving to the inflation here and how monetary policy reacts. And from the monetary theory, monetary policy, what we know, if inflation increases, monetary policy basically it reacts and it also increases. So let us see what basically happens here. So here you can see as the inflation, we have given in a positive of inflation, that is inflation increase. You can see as inflation increases, the monetary policy reacts. So we know that if inflation increases, monetary policy will be tightening to contain the inflation. And that's what basically here we are looking at. Okay, once we give the positive shock to inflation, the interest rate basically increases to contain the inflation. So it is also as per the expected theoretical expectation. So these all three we have seen that what happens. We can also one of the critical is that if the monetary policy takes decision, what happens with the output and what happens with the inflation. So here the idea is that if we give a positive shock to the inflation, that monetary policy, that is basically if you are tightening of the monetary policy, then inflation should subsidize. And we also know that if the monetary policy tightening, then there will be decrease in the output. So and basically we use the WAR model to see if the monetary policy takes decision, how it the output growth or economic growth and inflation reacts. So for that, let us take that we are uh, having SVR. So here basically we are seeing output gap. So that is how the output reacts. So we have wanted to IRF. Then here we have the model SVR node 1. Here we have, then we are giving impulse to the RRP, that is the monetary policy. And we wanted to see the response of output gap. Yeah. Then we wanted to plot that. So plot, and here we have saved as SVAR out. So let us see how it reacts. So here you can see that as the monetary policy tightens, because we are giving the positive shock, output decreases. and later on it increases. So there is again decrease and increase. So this is the so the first reaction we are seeing that, which is as per the theoretical expectation, if we tighten the monetary policy, the output will reduce. So that's basically here we are. Our theoretical, our model also predicts, which is as per the theoretical expectation. Now let us see what happens with the inflation. So as we are, let us say inflation one we are giving, because already we have inflation in response of the output gap. So IRF, then here we have SVR level 1, then we are here we are giving impulse to the policy rate, and here giving the response to the inflation. So as per the theoretical expectation, inflation should reduce. So let us plot SVR inflation. So here you can see that as we give a shock to the monetary policy, the inflation reduces. Then later on, the effect decreases and inflation further rises up. That means the monetary policy does have an impact on both on the output gap as well as on the inflation. That means if there is the inflation in the economy, monetary policy makers can increase the rate of interest, and they, by increasing rate of interest, they can contain the inflation. However, it has also a negative impact on the output, that is output will be decreased. So that's the basically balance we have. We have to make uh, to contain the inflation, how much inflation we want. So that's the basically the monetary policy makers has to make the decision. Then we know that another tool uh, to react to to check this vector regression or the structural vector regression is the forecast error variance decomposition. So what is the forecast error variance decomposition? This already we have discussed in the previous lectures. So for that, we have the function FEVD. So here we are taking the model. So n ahead is 10. So basically here, how much steps we are taking, how much, what horizon we are taking here, we are taking the 10 is ahead. So that's we are storing here. Then we can see the values here, that how much response if you are giving shock to the output. So how much variation in the output is explained by the output itself, how much variation in the inflation is explained by the output, and how much variation in the impulse interest rate is explained by the output. So here we can see that most of the variation in the output is explained by the output itself, and the further in the inflation and also in the monetary policy. Similarly, how much variation in the output is explained by the inflation, how much variation in the inflation is explained by the inflation itself, and how much variation in the monetary policy is reacted by that. The same information we can look by plotting that here. So this is the plot we'll get here. Okay. So here we can see that this is the percentage variation in the uh, output due to its output. So here you can see that here the markers you can see this lighter shade is the response of the policy rate, and this is little darker is about the inflation, and this is the most darker is the output gap. So here you can see most of the variation in the output is due to the shock to itself. However, here you can see in the inflation is in the first period, the, the share, the percentage change in the inflation is explained by its own shock. However, the second leg onwards, the highest variation in the inflation is explained by the change and the shock to the policy rate and output gap. So largest contributor to the variation in inflation is due to the output gap. Now, in the policy rate, you can see in the first leg, the largest contributor to the change in the policy rate is the policy rate itself. Then later on, we can see the influence of the output gap is increasing as the time passes. So that's the basically we can see here the variation in the output gap is largely explained by the variation in the output gap itself. However, in case of inflation and the policy rate, as the first yes in the first period shock, most of the variation is explained by its own shock. However, as the time passes, the shock of the output gap dominates, and the most of the variation in the inflation as well in the policy rate is explained by the output gap. So that's the basically structural vector autoregression. Uh, uh, you can compare that in terms of the explanation of the impulse response function, and the forecast error variance decomposition is same as we have done in the vector autoregression. However, how we estimate the model, how we create the restrictions, that is derived from the theory. And that's the basically the improvement we have in the structural vector autoregression in comparison to the vector autoregression. In the vector autoregression, those restrictions are theoretical, basically derived from the statistical theory purpose. However, in case of structural vector autoregression, those restrictions are drawn from the economic theory. That's why the structural vector autoregression is assumed or believed to be the superior than the vector autoregression. Uh, So if you have any query or the questions, you can ask me for further explanations, and we'll stop the sharing here. And here we'll have this. So thank you so much for joining this. If you have any queries, you can mail me or we can discuss on the discussion forum. Uh, I hope you have got the data and the codes. I will also try to share the script and the data for this particular class. Thank you so much. And we'll have one more live sessions on the 12th of April. So here we will be basically discussing about the some of the applications in of this course into the corporate world. So thank you so much.